Hi, I'm Gary, and I want to show you how I use Cloudy. So today we're going to talk about calculating the cooling function, what it is, and why we care about it. So in this field, heating is anything that gives kinetic energy to the thermal electrons. So we have the free electrons in the continuum referred to as the thermal electron. So thermal electrons can gain energy, heat them up, and they can lose energy. Anything that gives kinetic energy to the thermal electrons is heat. We talked about in the previous video, photonization does that because the instant photon has particular energy, 13.6 goes to EV, goes to liberating the electron. All the rest of the photon energy goes into the superthermal electron that then is shared with all the thermal electrons. So that heats up the electron bath. And we also saw that more energetic, more hotter stars will make more energetic photoelectrons, so you get more energy per photonization. Cooling is anything that removes thermal energy from the thermal electrons. And so this is mainly inelastic collisions where a free electron strikes, and often the most important case is O3 for nebulae, and that causes an orbiting electron to go to an excited state and then decay, making a photon. So it changes kinetic energy into thermal energy into light. So these two processes are the first one, it takes the energetic photon from the star and creates heat from that by photonization. The second process takes the kinetic energy in the free electrons, the thermal electrons, and goes back to make light. So it's light going into heating, then light going into cooling in many cases. So what we're going to do today is calculate a cooling function in the classical way, and this is done not in photoionization case, but in collisionalization case. This goes back to early studies of the sun. So in collisionalization, in this model, we're not even going to set a radiation field. So we're going to assume that some other process that we haven't gone into has established the temperature of the thermal electrons. So you can set that temperature then as a free parameter. So we have a new free parameter, the temperature of the electrons. And so there's two commands to do it. The coronal equilibrium command is sounds better. It's meant to do outer reaches of the sun, and that's where this physics was first developed in the 1960s. At constant temperature, this is pretty much the same thing, but it forces the free electrons, the thermal electrons, to have a certain temperature. And so this is described here. And so what we're going to do is set up a test case where we're going to specify a coronal equilibrium model. There's no light in this model, not even the CMB. And we're going to vary the temperature of this coronal temperature. So the grid goes from 100 Kelvin up to a billion Kelvin in a quarter dex steps. So we're going to get a series of models that are in collisionalization equilibrium, collisional coronal equilibrium at all these temperatures. The middle here is just setting up cloudy so that it will run, have a unit hydrogen density, and then it's going to make a unit cell of gas. Uh, that's just personal preference. We're going to save some output. The save continuum we've seen before, save grid we've seen before. The save cooling command is new. We'll look at the output in a second. And so what that saves is the cooling for this particular model and identifies what the most important coolants are. There is something different. We're using save continuum with a separate command. All of these save commands have a keyword separate that tells the code not to do the gather at the end. So the way this works, it counts how many performance cores the computer has, and it farms out one model on every core. And then when they're all finished, it gathers the files back together. So if you have a lot of save overview files, it will gather them together. So it looks like you just had one single calculation that went through a lot of models in a sequential run. That gather in a large number of models can be the most expensive step because you could have hundreds of megabytes out there and trying to work all these files isn't cheap. There's a separate command. So you see this on the save continuum separate. That means don't do the gather. Leave the files as they are on disk, and we'll see what comes of that. What we're going to do is we're going to look at the spectrum at this range of temperatures, and we're going to see how much the spectrum does change and what kind of light it produces. We always need to include cosmic rays when we go down to low temperatures. Cloudy will try to do the model without cosmic rays below about 4,000 Kelvin, but it will complain. It will let you know that it's not happy. This is the safe cooling output. We've not seen this before, so what I did is copy paste it into a spreadsheet just so we can see this is for this particular sim. Column B gives the temperature in a quarter dex steps, so you can see it coming up. The heating is given in column C, but that's irrelevant. We're forcing the temperature, so it's not going to be used. The cooling is what we're interested in. To make the cooling function, we want to make a plot showing the cooling as a function of temperature. So I've got that coming up next. This is the cooling fractions, column F. It shows you what ion, what species is producing what part of the cooling. And this is carbon 1 at 100 Kelvin. It is a very, very important coolant. At 1,000 Kelvin, it's SiO of all things. And then it's a different species can be the dominant coolant. So these are the species that are making the strongest emission lines at these temperatures. Well, if we just look at the safe cooling and look at the cooling as a function of temperature, we end up with this remarkable beast here. Uh, it's not monotonic. It's definitely not monotonic. And it has peaks and valleys. It's got one peak here, one here, one here. You can see this huge step size we took. If you wanted to do this professionally, you'd be do a much finer step size. But the overall shape here is pretty typical. You frequently will have a peak at about 1,000 Kelvin. 100,000 degree peak is another thing you find very often. And this tail, a high energy tail like that, is also something you see a lot. So what we're going to do is have a look, first of all, today at what kind of spectrum these different temperatures make. Next time, the next video, we're going to talk about what this complicated curve results in. It means we have several phases of the ISM. But first of all, let's look at the spectrum. So I used separate keyword on safe continuum, so the gather didn't happen. So we have this mess of coronal.conv files. And so all the grid points has a coronal.conv file. So how do you sort this out? These are the spectrum at different temperatures. Well, what you got to do is find this grid index, and then you go over to the grid output, and you look up what that grid index is, and it will tell you the temperature. So you could have a scripting program, say you wanted to do a spectrum at some temperature. You could use the grid to figure out what's the index for that temperature, and then use that index to get a spectrum. So this is a useful facility if we're going to do what we're going to do next, which is look at some spectra. So we're going from hot to cold. So this is 100 million Kelvin. The wavelength axis, so the visible light is right in the middle. This goes almost to the millimeter in the radio, and then in the high energy end, it goes into the hard X-rays. So at 1 million Kelvin, you wouldn't see this in the optical, not much. And there's strong lines in the hard X-ray, and this continuum here. So for 1 million degrees, if you look in the X-rays, you're probably going to see 10 million, 100 million degree gas. At 1 million degrees, this is very interesting. There should be gas here. We'll see this next time, but it's very, very hard to detect 1 million degree gas. The problem is you can see it doesn't emit much in the optical, doesn't emit in the IR. It's not zero. You can find lines down there, but they're going to be very hard to detect. It makes a lot of light in the ultra soft X-ray or the extreme ultraviolet, where the opacity of the interstellar medium is too great. We can't see out of the galaxy. So we'll probably never be able to observe in this region except for the very nearest stars or inside the solar system. So it's a disadvantageous part of the spectrum, but it's got a very, very rich, spectrum. Come down to 10,000 Kelvin. This is collisionalization, not photonization. You see it's got a lot of lines in the optical. This is almost certainly Lyman alpha. And it's got even stronger lines in the millimeter and submillimeter and infrared. So if you want to look at gas that cold, you want to look in the optical or into the infrared. It's a selection effect. If you only have a ground-based optical telescope, you're most effectively going to be picking out gas at 10 to the 4 Kelvin. That doesn't mean that's all that's out there. It's a selection effect. You can't see the other phases. Then all the way rock bottom to 100 Kelvin, the save cooling file showed the SIO can be important down here, but it's not a rich molecular spectrum. It's very, very difficult to form molecules at low temperatures if you don't have dust. And we'll add dust later on and see what that does. So it's not a very, very rich spectrum. The problem at low temperatures is the interstellar medium is a cryogenic vacuum, and every chemist knows that there's no chemistry in a cryogenic vacuum. And so it's a challenge, but the cosmic rays provide a way out. So what we're going to do from here is build on this. In the next video, talk about the stability of these different parts of the cooling function, and then what happens in a nebula if you change the heating rate and it has to adjust its temperature. So see you then.